Alright, so we're looking at section 2.5, and section 2.5 deals with zeros of polynomials. And what we're looking for is we're looking for ways to find the zeros of polynomials. Alright, so we've got different types of zeros of polynomials, and it all depends on what type of coefficient that polynomial has. So let's look at a couple of different examples here. A polynomial can have numbers like this over here, and if one of the coefficients is imaginary or complex, then it's a complex coefficient. That means that you're going to have imaginary numbers introduced into your zeros somewhere in there. Now, that doesn't always mean that's the only way you know that, but you know that if you have complex coefficients, you're going to have complex numbers in your zeros. Now, you can also have a polynomial where all the coefficients are real. Now remember, the square root of 2 is real, but it's not rational. It is an irrational number. Pi, same thing. Now notice that we've got x, it's still to the first power. Remember, we had the rule that said if we have x to any power that is negative or not an integer, then it's not a polynomial. Well, this one is a polynomial. X to the third, x squared, x to the first, x to the 0. We don't have any square roots of x or anything like that. This is just the square root of 2. So that's okay. And all these coefficients are within the real number system. Now we can be more specific, and we can get a situation like this where every one of our coefficients are not only in the real number system, but they're all rational. Remember, a rational number is a number that you can express as a fraction. So 5 can be thought of as 5 over 1, 3 over 1, of course 1/2 and 3/8. Hopefully those are self-explanatory about being expressed as a fraction. But those are all rational numbers. So at that point, we've limited our polynomial down to the point where we only have rational exponents. And there's or rational coefficients, sorry. And there's one more step, and that's where they're all going to be integer, where your coefficients for all of your terms are going to be integers. Remember, that's a whole number, positive or negative, that you can have as the number in front of your x to the third, x squared, x to the 0, or whatever you've got there. Now remember, this does not change the definition of a polynomial. We cannot have x to a negative power, and we cannot have x to a rational power or an irrational power. All the powers of x, our exponents, must all be positive integers or 0. All right, now the Rational Zero Theorem says that if we have the polynomial f of x equals a(n) to the x to the nth power times x to the nth power plus a sub n minus 1 times x to the n minus 1 power plus ... a sub 1 x to the first power, understood there, plus a sub 0, and all these things are integer coefficients, a sub n minus 1, all the way down to a sub 1 and a sub 0 are all integers, then every rational zero of f of x is of the form p over q, where p is a factor of the constant a sub 0, the constant over here with no x attached to it, and q is a factor of the leading coefficient a sub n over here. Now, we've done some of these, but we're going to do some more, but this is the way that you limit your choices to every possible number on the face of the earth down to a list that you're going to make. Now, don't forget, this is just a math way of defining every single possible polynomial that you can have. That's what the ... is. This could be n to the first power, n to the second power, n to the 10 millionth power. It doesn't matter. This denotes every polynomial you're ever going to see. All right, so if q is the leading coefficient and p is the constant term of the polynomial, then the only possible rational roots are plus and minus factors of p divided by plus or minus factors of q. That's where you get the p over q. So for example, if we were to look at this right here, and we wanted to find all the possible rational roots, or possible rational zeros, we're going to do plus or minus. One plus or minus out in front takes care of all of it, really. And then you're going to look at all the factors of 4, which is 1, 2, and 4. There are your factors of p. And your factors of q, 6, is 1, 2, 3, and 6. And now all you want to do is you want to make every possible combination you can have. So you got 1 over 1, you got 2 over 1, you got 4 over 1, and then you're going to have 1 over 2, you're going to have 2 over 2, which is 1, I already have it. You're going to have 4 over 2, which is 2, I already have it. Then you're going to have 4 over 1, or sorry, you're going to have 1 over 3. You're going to have 2 over 3. And you're going to have 4 over 3. All right, so that's got all the top over 3. Now do all the top over 6. So you're going to have 1/6, 2/6, which is 1/3 I already have, and 4/6, which is 2/3 I already have. So now I've taken every possible number, infinity, that might divide into this and be a 0, and I've limited it down to 1, 2, 3, 4, 5, 6, 7, 8, plus and 8 minus, so I've limited it down to 16. Now even though you've still got quite a bit of work here to find the ones that would work, you got to admit going from infinite choices down to 16 is a pretty good step. And those are going to find only the rational roots. If you have complex roots or you have irrational roots, this will not find it. How are you going to find imaginary or complex in that list right there? It's not there. But if you have rational roots, this thing will find it. Guaranteed, any rational roots that are part of this polynomial are in that list right there. Now, to find the possible rational roots of x, we need the factors of the leading coefficient and the factors of the constant term, and the possible rational roots as we just found are all that list right there. All right, so you guys try this one and list all the possible rational zeros of x cubed plus 2x squared minus 5x minus 6. I'm going to pause the video and I'll work it out, and then I'll come back and you can check your answers. So I want you to pause the video, work the problem out, and then when you're ready, come back and check your answers. I'll show you the answer in 3, 2, 1. All right, this one was an easy one. Usually when you've got a 1 out front, it actually turns out to be real easy. It's just all the factors of this one. So we've got plus or minus all the factors of 6, 1, 2, 3, and 6 over all the factors of 1. Well, there's only one factor of 1, that is 1. So you get the possible factors of plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So out of infinite choices for zeros that you could, if you're shooting blind, trying to find this thing and solve it, you're now down to 8 choices. All right, you guys try this one, and like I did before, I'm gonna pause it, work it out, and then I'll come back and show you the answer. And I want you to pause it, work it out, and come back and check your answers. So I'll show you the answer in 3, 2, 1. All right, so here's the answers. Your possible rational zeros are all the factors of 3 over all the factors of 4. So you end up with, when you simplify this down, plus or minus 1, plus or minus 3, plus or minus 1/2, plus or minus 3/2, plus or minus 1/4, and plus or minus 3/4. So once again, from every possible number on the number line and in between the numbers on the number line, you get down to what is this? 1, 2, 6, 12 options. So it takes a huge amount of work out of this. All right, so how do we know which of the solutions are really zeros or solutions to this thing? Well, we can use trial and error, synthetic division to see if one of the possible zeros is actually a zero. Remember, when you're dividing by x minus c, if the remainder is 0, when using synthetic division or long division, either one, then c is the 0 of the polynomial. So if you divide it out and the remainder is 0, then it divided in evenly, therefore it's a factor. And it's a 0. If it's a factor, then you can solve it to be a 0. If c is a 0, then solve the polynomial resulting from the synthetic division to find the other zeros. In other words, don't go back and start with the same polynomial again. Once you do your division, let me give you an example here. Let's say we divided 2 into something, let's say A, B, C, D, and then let me go one further, E, and then we do our division and we end up getting F, G, H, I, and then we get a 0 right there for your remainder. Use this polynomial right here to work from there. You've already got the 2 and divided it out. It's a factor. You've pulled it out. Don't go back and use this big, ugly polynomial to look for the other ones. Use the simpler one. It makes things a lot easier and a lot quicker. All right, so to find the rational zeros of a polynomial, you're going to list all the possible rational zeros of the polynomial using the Rational Zero Theorem, like we've just done. And then you're going to use synthetic division on each possible rational zero, and the polynomial until 1 is going to give you a remainder of 0. This means that you have found a 0 as well as a factor. And then you're going to write the polynomial as the product of this factor and the quotient. Remember, the quotient's the answer to the problem. That would be the FGHI that we're just looking at. That's the quotient. And then you're going to repeat this procedure on the quotient until the quotient is a quadratic. Once it's a quadratic, remember that's a degree 2, you can either factor it or you can use the quadratic formula. So once you get it down to a quadratic, it's easy to deal with. And the good thing about having it down as a quadratic and using the quadratic formula is that the quadratic formula will find all the remaining real, even if they're irrational, zeros, and any imaginary zeros at the same time. All right, so let's find all the zeros of x cubed plus 8x squared plus 11x minus 20. So first things first, let's list all the possible rational zeros. When we do that, we're going to take all the factors of 20. So 1, 2, 4, 5, 10, and 20 over all the factors of the 1 in front. So of course we're just going to have all that list plus or minus. Plus or minus 1, 2, 4, 5, 10, and 20. All right, so at this point you want to go ahead and start doing your synthetic division unless there's another way that you can get a little hint. Sometimes with the more complicated ones I may give you a graph or something like that. And if you look at the graph, remember the zeros are going to be wherever it crosses. So if I had something like this, let's say 1's right there, I've got a 0 right there that looks like it might be at 2. So I would definitely want to choose 2. This is not the graph of this thing, guys. I'm just giving an example. All right, so let's try 2. We'll try positive 2, and we're going to have 1, 8, 11, and negative 20. So we bring this one down, so you got 1 times 2 gives you 2. Add those, you get 10, that gives you 20, and this is not going to give me 0. Because when you add those together, you're going to get 31. Of course, that's going to be a number way bigger than 20. That would make that 0. So let's go ahead and erase that. While we're with the 2, let's go ahead and do a negative. So you might want to go ahead and list these out. So let's do that one, the positive, and let's do negative 1, 2, 4. I don't know why I'm writing 3, 5, 10, and 20. So I know 2 does not work, so I can go ahead and mark it out. So let's try negative 2. And if I try negative 2, I'm going to get a negative 2. Oh, no, I'm not. Pay attention here. I'm going to get a 1 there. I'm going to get a negative 2 here. Add that, I get 6, negative 12, and that's going to give me 1, negative 1, and that's going to give me positive 2, which is not going to give me 0. So I can go ahead and erase that. And yes, you're going to have to do this a couple of times, unless you're just lucky and pick the one that works right off the bat. All right, let's try the positive 1. Actually, while we got a negative, let's go ahead and do negative 1. We've got 1, negative 1, 7, negative 7, 4, negative 4, and of course that's not going to be 0. So negative 1 does not work. Okay, positive 1, I'm guessing it's not going to work either. 1, 1, 1, 9, 9, oh, hold on now. 20 and 20. Looky there. So there is one that worked, literally, positive 1. Now what it means to write it as the factor and the quotient. Well, right here's the quotient. Here's the factor, but it's in solved form. Remember, this is x equals 1. So what would you do to get it over on the other side and get it equal to 0? You'd move the 1 over by subtracting. So you're going to get x minus 1. There's your factor. And then write this out as your polynomial. You're going to have 20 as your constant, 9 as your coefficient for your x, and 1 is your coefficient for your x squared. So you're going to have x squared plus 9x plus 20. All right, so at this point right here, we've got what? We've got a quadratic. So we can try to factor this. So I'm going to do x minus 1, just bring it down, because it's got to be part of your answer. What your answer is has to be all the factors that would multiply to get this thing right here. X minus 1 continues on through. All right, so let's try to factor here. Plus here means we're going to have same signs. They're both going to be this sign right here, so plus plus. The factors of 20 that will add to give me 9 are 5 and 4. So 4 there, 5 there. So right here are all the factors. There are all the factors. Now what are all the zeros? Well, remember, for the zeros, you're just going to set this thing equal to 0 and set each one of these equal to 0 as well. So what are the zeros? X equals 1. Move the 4 over. It's going to be negative 4 and negative 5. So there are your zeros. These are your factors. These are your zeros. So make sure you give it in the form that it's asked for. I will always, 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 when I'm doing the work, I will find all the factors. Then if I have to take it to the zeros, it's real easy to do. Remember, you're just moving that to the other side and changing the sign. But I'm always going to factor it completely, because you're not always going to have looking for the zeros. So I just get in the habit of factoring it. Once I got it factored, I know the zeros. All right, so I want you guys to try this one. I'll work with you for a little bit to get you all the possible rational zeros. And by the way, this one's going to be really easy because you're going to have like 4 choices. So the possible rational zeros are going to be plus or minus all the factors of 2. Ooh, that's tough. 1 and 2. And all the factors of 1, which is, well, 1. So you literally have plus or minus 1 and 2. So you have 1, you have 2, you have negative 1, you have negative 2 as your choices. So those are the ones you're going to work on. So I'm going to let you guys, I'm going to pause it, let you guys work this out. Try it. Try it. That's what's important about this. You've got to actually try it yourself so you know what you don't know and you know what questions you need to ask. So try it, and I'll show you the answer in 3, 2, 1. All right, so I'm starting it back a little early, but I wanted you to get to here, definitely get to here. So you know you've got a 0 that's going to be positive 2. And this one, I'm imagining that when you tried to factor it, you kind of hit stop. Because what happens if you got x and x, same signs, both plus, 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 what are the numbers that multiply to give me 1 but add to give me 3? There are none. You could have 1 and 1, but that would have to be 2. So this thing does not factor. That is where you have to use the quadratic formula now. So let's use the quadratic formula. Remember, it's finding out what x is. So this is the only factor we have. This is not factorable anymore without getting into imaginary numbers. So we're looking for the zeros. So when we solve the quadratic formula, remember x equals means we're finding the zeros. And that is negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember, 1 is my a, 3 is my b, 1 is my c. So when we go to solve this, we plug in all that in, we're going to get negative 3 plus or minus the square root of b squared, which is 9, minus 4 times 1 times 1. And that is all over 2 times my a, which is 1. Now, I've got negative 3 plus or minus. Simplify the square root here. We've got 9 minus 4, which is going to be the square root of 5, over 2. Now, that is an irrational number. And how many numbers do I actually have there? Remember, I have 2. I have negative 3 plus the square root of 5 and negative 3 minus the square root of 5, all divided by 2. So when we list our zeros, if you don't put the plus or minus, you can actually list this. What's the 0 that comes from here? It'd be positive 2, so x equals 2. And then the 2 that we get from right here, negative 3 plus or minus the square root of 5 over 2, or you could write it negative 3 plus the square root of 5 over 2 and negative 3 minus the square root of 5 over 2 if you wanted to write all 3 of them out long. Either way is perfectly okay. Just don't forget to put the plus or minus if you're combining them together. All right, so how many zeros does a polynomial with rational coefficients have? Well, an nth degree polynomial has a total of n zeros. So the power for the leading term, the one that has the highest degree, is going to tell you how many zeros you have. Now, the thing is, though, some of these zeros may be rational, which is good, irrational, which is okay, and complex, which is, the ones that we're not actually going to see on a graph. These two we'll actually see if we were to graph the thing. It's still going to be an x-intercept. This one you're not going to see on a graph. Remember, these two are going to show up as x-intercepts and where the graph crosses the x-axis. This one, not so much. It doesn't show up at all. Now, because all coefficients are rational, irrational roots will exist in pairs, both the irrational number and its conjugate, and complex roots also exist in pairs, both the complex number and its conjugate. Now, what that means is that if you have if you have a polynomial with rational coefficients, it has to have rational coefficients. If it doesn't, this doesn't work. If it has rational coefficients, then irrational roots are going to exist in pairs. You're going to have a number and its conjugate. And here's a example of a complex root, a plus bi, and its conjugate, a minus bi. So if you have coefficients that are rational, expressed as a fraction, you know, not imaginary numbers and not irrational numbers, then your complex roots and your irrational roots are going to exist in pairs. Now, we saw that right here. Because what kind of root or what kind of zero is that right there? Well, it's not imaginary because we're not taking the square root of 5, but the square root of 5 is not a whole number, and that's going to be one of those decimals that repeats forever and ever and ever. So this is actually an irrational root. And what do we know? They occurred in pairs. Negative 3 plus the square root of 5, negative 3 minus the square root of 5 over the 2. So they are going to occur in pairs as long as the coefficients of the original polynomial are all rational numbers. All right, and with the irrational numbers, here's an example of an irrational number and its conjugate. A plus the square root of b and a minus the square root of b. That's the one we just saw with the last example. All right, now sometimes it's going to be helpful, especially for the ones that have really high degrees, to graph the function and then find the x-intercepts, which are the zeros, to narrow down all the possible zeros. If you've got a PRZ that you find and you have 24 possible zeros, guys, I'm not going to ask you to do that by hand. I'm going to either give you a graph or I'll let you have a calculator to be able to graph it. You're looking for where it crosses the x-axis. Now, does that mean you're not going to have to show me all the work that goes along with it? No, it does not. You're still going to have to show me the long division or the synthetic division that proves that those y-intercept or x-intercepts are zeros, and that's going to break down that polynomial. And then once you get the polynomial broken down to where it's a quadratic, then you can move a lot easier with it. All right, so let's solve this one. We got x to the fourth minus 6x cubed plus 22x squared plus 30x plus 13 equals 0. So we're still going to solve this the same way. Let's go ahead and list the PRZs. We got plus or minus all the factors of 13. Wow, that's tough. 1 and 13. And all the factors of 1, which is 1. So we have plus or minus 1 and 13. So let's go ahead and list it over here. Negative 1, negative 13. And we're going to do our division. And we got 1, negative 6, 22, negative 30, and 13. And we're looking for 0 here. And just drop that one down. Now what do we want to try first? Let's try negative 1. If we try negative 1, we're going to have 1 here. 1 times negative 1 gives me negative 1. That's going to give me negative 7. That's going to give me positive 7. That's going to give me 29. That's going to give me negative 29. And that's going to give me negative 59. So I don't think that negative 1 times negative 59 and then add that to 13 is going to give me 0. So we can get rid of that one. All right, so, well, while we're with ones, let's try the positive one. So bring 1 down. 1 times 1 gives me 1. It gives me negative 5. Negative 5 gives me 17. Give me 17. That's going to give me negative 13. And that's going to give me negative 13, which does give me 0. So I know that x minus 1 is one of my factors. And I have 1, negative 5, 17, and negative 13, which gives me x cubed minus 5x squared plus 17 minus 13. All right, now I'm still not down to a quadratic, so I'm going to have to do something else here. And what I'm going to do is just do the same thing over again. I'm going to take just this polynomial, and I'm going to list its PRZs. And guess what? They're going to be exactly the same. So plus or minus 1 and 13. Now here's the thing. Guys, understand this. When I tried the negative 1 up here, if it didn't divide in evenly, it's not a factor of this group. So that means that it's not going to factor here. Now does that mean that x minus 1 won't factor again? No, we may, or x plus 1, sorry, that 1 won't divide in again? No, it doesn't. We could try it, and it may, and that if it occurs as a double root, then it will work. But once we identify one that does not work, like this one, we don't try it again. Because if it doesn't divide out of the original one, it's not going to divide out of any step along the way. If it does, you've done something wrong. All right, so we're down to 1, 13, and negative 13. Let's go ahead and get the 1 out of the way while we're at it. And I'm going to come back and show you a little trick on how I do this, just to kind of keep it continuous. But I'm going to go ahead and work it first. So you got 1, and you got 1, negative 5, 17, and negative 13. And you're going to drop the 1, 1, 1, negative 4, negative 4, and looky here, 13, 13, and 0. So 1 did actually work twice. So now from this, what do we know? We've got to bring this 0 down. So we've got x minus 1. We've got to bring this 0 down. We've got another x minus 1. And then we've got this polynomial right here, which is x squared minus 4x plus 13. And this thing is, remember, it's set equal to 0 up here. So even down here, this is equal to 0, and I didn't write it here. So we're looking for all the zeros, which means we've got to factor this, and let's see if we can factor it. I'll factor it right here if I can. X and x. I'm going to go out on a limb and say this probably is not going to factor. Factors of 13 are 1 and 13, and they do not add to give me 4. So I'm going to have to use quadratic formula again. So let's go ahead and do it right here. I'll change colors. We've got x is equal to negative 4, which gives me 4, plus or minus the square root of b squared, negative 4 squared is 16, minus 4 times a, which is 1, times c, which is 13. And that's going to be all over 2 times 1. Now, when we go to simplify here, we're going to have 4 plus or minus square root of 16. Well, 4 times 13 is, 4 times 10 is 40. 4 times 13 is 12. You end up with 52. So you end up with 16 minus 52. And when you do that, you're going to get what? Negative 36. Yeah, you get negative 36. So we've got the square root of negative 36 over 2. All right, and remember with the negative, we're going to have to get into imaginary numbers. So we've got 4 plus or minus. What is the square root of negative 36? It's 6i. And over 2. Remember, if the 2 will divide into both the real part and the complex part, coefficient-wise, not inside the radical, but outside, you can actually simplify this. So 2 will go into 4 and give you 2. 2 will go into 6 and give you 3i. And it's plus or minus. So my zeros here, when I solve them, are 1 from here, a 1 from here. So I got 1 occurring twice. I don't have to write them twice, though, unless you just want to. If you do, I'm not going to count off. And then the imaginary root or the imaginary 0, is 2 plus or minus 3i. So that's how you break them down. Now, I told you I was going to show you a little trick that I use, and it would go back right up here. If I know I'm breaking this thing down all the way, I would not continue like this. I would never stop there. What I would have done is I would have continued on right here doing my synthetic division. Let me change my colors here and do this in red. This is how I would have done it. If I was going to try the 1 again, I would have done the 1 right there. I would have come down here, and I would have done my synthetic division as one continual thing. It almost kind of looks like long division, but it's doing the synthetic division over and over and over again. So you got 1, 1, negative 4, negative 4, 13, 13, 0. And so you still get the same thing. But you've already got those numbers written, so I'm thinking, why not just use those? You do not use the remainder over here. Remember, once the remainder is 0, that goes away. You ignore that. So you're dividing this 1 into literally that polynomial that we just have as the quotient. So that's how I do it. You're more than welcome to do that, to steal that and use it if you want to. I don't care. And then notice right here, you get the same thing we got down here that we had to end up using the quadratic formula for anyway. All right, so remember, for a polynomial with all real coefficients, complex zeros must come in pairs as complex conjugates, a plus bi and a minus bi. Now, it may be over a 2 or something like that. That's perfectly okay. But they have to come in conjugate pairs as long as you start off with a polynomial with all real coefficients. And irrational zeros are also going to come in pairs. So if you end up with a square root in one, you're going to end up with a square root in the other one as well. You have to have a pair of square roots. Otherwise, the square roots don't go away. Same thing here. If you FOIL this out, guess what? The I goes away. If you FOIL these two out, guess what? The square root goes away. But if you don't have those conjugate pairs, then that doesn't happen. And you end up with a I or a square root in your polynomial, which, once again, we're starting off with knowing that the polynomial has all real coefficients. All right, so find a polynomial function in factored form of degree 3 with 2 and I as zeros. All right, so start off with what you know. You know that x is equal to 2. That's one of your zeros. I is another 0, and guess what? If I is 1, then negative I is 1 as well. Remember, they have to come in conjugate pairs. So you want the polynomial function in factored form, so just change these over to factors. Move that one over, you get x minus 2. Move that one over, you're going to get x minus I. Move that one over, you're going to get x plus I. Now notice your conjugate pairs there. So there's your polynomial you're looking for. Don't make things harder than they are.